systems in a lot more detail. But anyway, just starting off, you only have two choices. The system's either a reaction or an object. And since this system is a reaction, then this is the way we handle it. All reactions have an initial temperature and a final temperature the same. And all that heat is going to go into the surroundings. So it should absorb the same amount of heat. I've got to keep the... And so the product solution and the calorimeter originally started off at room temperature, but are going to end up at, well, not room temperature is whatever temperature you measure, not necessarily 25, but the temperature that you're monitoring. And then it's going to stay as product solution and calorimeter at T hot, or T mix. This is a cue of the surroundings. Now, product solution is product solution. It didn't change. The only thing that happened to the product solution is it warmed up. The calorimeter it didn't change. It didn't go any kind of chemical change, right? There was no chemical change. This is just a physical process. You take two objects and you warm them up. That's all that happened, right? Once the reactions stop, then that's it for chemical changes. To answer the earlier question. All right, so we just have to figure out the system and the surroundings. When we mix these two together, how many milliliters do we get? 100.0 milliliters of NaClAq. Plus, there's going to be a little bit of excess HCl. And then this is going to be capped. We're going to monitor the temperature. Same type of deal. Hopefully, what we'll observe here is that the two temperatures for the solution are the same. They should be the same. But that doesn't always happen. It doesn't always happen because maybe somebody just took one of the solutions and moved it to someplace else, or the two temperature probes aren't giving the same reading. But it would be nice if they just overlapped here, like this. Okay, then we mix the two solutions together. We're going to mix it, and then we'll keep it with the purple thermometer here. Purple thermometer is going to jump up in temperature here. The blue thermometer is still going to, well, it's going to go from solution to air. I think the air temperature is probably warmer or cooler. If it's warmer, it'd pop up. If it's cooler, it drops down. Or if it's the same temperature, it'll stay the same. And then we monitor the progress of this reaction until we see a nice, smooth cooling curve. Like this. Let me erase that. So the last good data point is at 5 minutes, right? Let's call this minute 6. I'm missing one data point, but that's okay. Are these data points at minute 6 good? No, we ignore those. And not only that, at minute 7, etc., it's probably not that good, so we'll just do something like this. And we're going to read off the temperatures off the ground. So this is T final. This is the maximum temperature that the surroundings reach. Right? We actually don't observe the maximum temperature the surroundings reach because it's already started cooling immediately when we mix the first drop, of HCl with the sodium hydroxide. And so we never really achieved that. And so what we're going to do is we're going to back extrapolate and see what it is. Well, it looks like we exceeded it here. Did we? Really? No. What was this probably due to? Yeah, incomplete mixing, a hot spot, a cold spot. Hot and cold spot. All right, today I've already seen, and every semester I see graphs like this. You know, even though I talk about this, I don't know what to do about graphs like this. Every semester, including this morning. Or how's that? And so what they do is they just get the temperature. That's my final temperature. That's my initial temperature. You know, the purple and blue. Does that look good to you? This looks awful to me. So please don't do that. All right. Once we get those temperatures, now we know what the delta T is, and that's the delta T for what? Is that the delta T for the system? Or is that the delta T for the surroundings, or for both?
Surroundings.
Only the surroundings. Remember, the system appeared and disappeared. And so, well, what is the system? The system is Q of the reaction. Q of the reaction is equal to what? Let's write it over here. A little bit bigger. Q of the system is Q of the reaction. Q of the reaction is the amount times delta U or delta H. Are we doing this in a bomb, or are we doing this in the open lab? And so, in other words, is the pressure inside the coffee cups the same as the pressure outside? If it is, then it's delta H, constant pressure. Now, sometimes delta U and delta H are the same. We'll talk about that tomorrow. That's what makes thermo complicated, you know, because it's not always different. And so Q of the reaction is equal to minus Q of the surroundings. What are the surroundings? This. The calorimeter and the product solution. So the product solution is just the sodium chloride AQ plus, you know, dot, dot, dot. The product solution plus the calorimeter. That takes care of the whole rest of the universe. And so the product solution is an object, right? Objects get hot, so this is going to be the amount times C times delta T. You know, the delta T. A lot of people try to do a delta T over here, but you know, what was the temperature? Was it hot sodium hydroxide and hot HCl that warmed up the surroundings? No, it was room temperature. And so here, we'll just finish this. The calorimeter is C-cal times delta T. All right, so the amount here is, well, the limiting reagent was 50.0 milliliters of 1.00 molar sodium hydroxide. And so this gives us 0.0500 moles of sodium hydroxide. So that's the amount of sodium hydroxide we have. Delta H we don't have, that's what we're solving for. The amount, what's this amount of sodium chloride solution? What's the amount of product solution? Take a look at it again. How much product solution do we have?
I wanted to ask about where you have 50.0 milliliters in the conversion factor as liters in college.
Mm-hmm.
You don't have to make it.
Oh, we have to cancel it out. So I just added one more. I was running out of room, so I didn't add it. We need the 1 liter is equivalent to 1,000 milliliters to get it to cancel. So what is the amount of product solution? 100, yeah. This is going to be 100.0 milliliters. What is C? We're going to assume it's close to water. But water is 4.18 joules per gram degree C. We have milliliters. This is milliliters of product solution. It's not milliliters of pure water. And so what is the density of the product solution? And so we have to make one more assumption here. We're going to assume that the density of the product solution is about the same as the density of water. If we make this assumption, then we'll have 100 grams here. And delta T. And so we're going to solve for delta H. The units for delta H are going to be in kilojoules per mole. Basically. We'll get the joules over here. We'll divide by the amount, which is in moles. This is going to come out a big number, which will convert joules to kilojoules. So are there any questions on this calculation here? All right, do you want to talk about the procedure in the lab first or take a break? Well, let's take a break. Let's take a